This program is about feedback, and we'll be looking at many of the circuits and dealing with many of the ideas which come up in Unit 6. We'll start off with the use of frequency response plots with feedback circuits. This is a simple voltage-derived series feedback circuit of the type I've dealt with in Unit 6. The amplifier has a single lag response and an open loop gain of 10,000. This is the feedback voltage divider. The circuit is fed from a swept frequency sine wave source. It produces a sine wave whose frequency slowly increases from a few tens of hertz to somewhat over 1 megahertz. The output of the amplifier is connected to this display unit. First, I want to look at the open loop gain. So I'll remove the top resistor R1. There is now nothing fed back to the inverting input, which is connected to earth via R2. R2 is a 1 kilo ohm resistor which is actually behind the board. I'll start the sweep generator. The display shows us the modulus of the gain against frequency, both on a log scale. So the gain is in dB. You should be quite familiar with this kind of graph by now. I can read the important values of gain and frequency off the display, and I'll ask Nick Heap to sketch and label each curve it is traced out. But since the system takes rather a long time to trace out each curve, I'll start the next one before asking Nick to sketch the first. This time, I'll close the loop by plugging in R1, which I've chosen to be 99 kilo ohm. Now I'll start the sweep again. Now back to the first curve. This horizontal portion is the open loop gain. It's 80 dB, that's a gain of about 10,000. The gain has dropped by about 3 dB, that's a 3 dB point here, at a frequency of 100 hertz. And the gain drops to unity, that's 0 dB, at this point, which is at around 1 megahertz. I confess that I've designed this circuit to give nice round figures to make life easier for me. Right, Nick, can you please sketch and label this first curve?
Well, the horizontal bit was at a gain of 80 dB, and the 3 dB frequency was at 100 hertz. It's about here. And it was 0 dB at 1 megahertz. I'm going to use just a straight 2 lines to approximate the frequency response of the amplifier. And I'll label this open loop.
Now for the second curve with R1 equal to 99 kilo ohm. The gain for the horizontal bit is 40 dB, that's 100. The 3 dB frequency is at about 10 kilohertz. Then the two curves join together. I'll just plug in a second value of R1. I'll use 9 kilo ohms. And I'll start the sweep. Okay, Nick?
Yes, the gain was 40 dB over the flat portion, and the 3 dB frequency was 10 kilohertz. It's about here. And again, I'll use just the 2 straight lines to approximate the response. And I know it went to 0 dB at 1 megahertz. I'll label this 99 kilo ohms.
Right, now with R1 equal to 9 kilo ohms, we have a flat portion gain of about 20 dB, that's a gain of 10, with a 3 dB frequency here of about 100 kilohertz. Then the 3 curves run together.
So a gain of 20 dB up to here, that's 100 kilohertz. And I'll use the straight line approximation again. And I know it goes to 0 dB at 1 megahertz. I'll label this curve 9 kilo ohms. Now, let's see how this fits in with the theory of the unit. The feedback fraction beta is equal to R2 over R1 plus R2. and R2 was 1 kilo ohm. So with R1 equal to 99 kilo ohm, beta is equal to 1 over 1 plus 99. That's 1/100th, and the gain was about 100. That's 1 over beta. With R1 equal to 9 kilo ohms, and R2 1 kilo ohm, beta is equal to 1 over 1 plus 9. That's 1/10, and the gain was about 10. That fits in with the unit. The gain is approximately equal to 1 over beta, the feedback fraction, provided beta times the open loop gain A is large compared with 1. Well, let's see. A was 10,000, and our smallest value of beta was 100th, and so the product, beta times A, is equal to 100. So we're okay to 1 part in 100. Now, what about the 3 dB bandwidth? Well, let's have a look. Here, it's 100 hertz, here, 10 kilohertz, and here, 100 kilohertz. But the thing to notice is that the product of gain and bandwidth is constant. It's 10,000 times 100 here, and that's a megahertz. Here, the gain is 100 times 10,000. That's also equal to a megahertz. And in this case, the gain is 10 times 100 kilohertz, and that's also 1 megahertz. So as feedback decreases the gain, it increases the bandwidth so as to keep the gain bandwidth product constant. So negative feedback allows us to control the gain of an amplifier. We get the gain we want by choosing the appropriate values for beta, and this can be done by choosing suitable resistors. But because the gain bandwidth product does not change with feedback for the single lag amplifier we have been looking at, increasing the bandwidth means decreasing the gain and vice versa. A single amplifier may not be able to give you both the gain and the bandwidth you require. If this is the case, you may need to use more than one amplifier, or to replace your amplifier with one that has a larger gain bandwidth product. Well, that's all we want to say about bandwidth in this program, but we'll take a further look at gain.
When we talk of amplifier gain in the course, most of the time we're interested in the voltage gain, the ratio of output voltage to input voltage. But amplifiers often change the magnitude of the signal current. They also change the power level of the signal, and that, in fact, is usually the most important function. Voltage, current, and power gain are all interrelated, and this can lead to confusion. In particular, I think the way that electronic engineers sometimes talk of voltage and current amplifiers can be misleading. We're now going to look at two circuits, one which has a definite voltage gain and another which has a definite current gain. The idea is to see how they differ in terms of what they do. This is the shunt feedback amplifier I've dealt with in the unit, the one with the virtual earth here. You may remember that the voltage gain of the amplifier is just this resistance divided by this resistance. But never mind the actual value of the voltage gain. What I want to investigate is how it changes when I connect various loads across the output of the amplifier. At present, there is no load, so the output's open circuit. The input voltage is shown on this trace, and the output voltage on this one. The voltage gain is the ratio of these traces, so the gain will change if one of the traces changes. I'll plug in a 10 kilo ohm resistor. Well, the traces don't change. I'll try 1 kilo ohm. No change. 100 ohms. Still no change. 47 ohms. No change. 22 ohms. It's beginning to change. I'll waggle it in and out so you can see that it's changing. So the voltage gain starts changing appreciably when the load is somewhere between 47 and 22 ohms. In order to see what this means, let's look at the Thevenin equivalent of the amplifier output circuit. The output of the amplifier is shown as voltage source V0 in series with output resistance R0. The load, RL, draws output current I0. And this current causes a voltage drop across R0. If the load does not affect the gain, then the volts dropped across R0 must be very small compared with volts dropped across RL. In other words, R0 must be very much less than RL. The smallest value of RL which did not affect the gain was 47 ohms. So R0 is very much less than 47 ohms. But the amplifier we used in the circuit was a 741, which has an open loop output resistance of about 75 ohms. So feedback has led to a considerable reduction in the output resistance. And it is this relatively small resistance which leads us to think of the circuit as a voltage amplifier, because provided the load resistance is 47 ohms or more, the voltage gain of the amplifier does not depend on the resistance of the load. Now, what about the current gain of this amplifier? This can show either the input current or the output current. To make things easy, I've chosen an input voltage that gives a current of 0.1 milliamps. And it does so for all values of load resistance. This means that the current gain is equal to the output current multiplied by 10, provided this output current is also measured in milliamps. Now, I'll put a 47 ohm load in, and we'll look at the output current. The meter takes a while to settle into its final value. In fact, it's about 5.1, call it 5 milliamps. So multiplying that by 10, we've got a gain of about 50. Now I'll try 1 kilo ohm. Now the current has settled to about 0.27. So the gain, 0.26 in fact is settled to, yes, so the gain is 2.6. Well, what about 10 kilo ohms? And now we're getting a current, well, it's less than the input current, it's 0.03. So in fact, we've got a gain of 0.3. And of course, when the amplifier is open-circuited, there's going to be no current, so the current gain is going to be 0. Well, the current gain varies from about 50 to nothing as the load goes from 47 ohms to open circuit. The variation is just what one would expect, because the output current I0 is just equal to the output voltage divided by the load resistance. If the voltage gain, and hence VL, don't change with load, the current gain must change inversely as the load resistance. We tend to call the amplifier a voltage amplifier because its voltage gain is well defined and does not change with load. But the fact that it amplifies voltage does not mean that it has no current gain. Far from it. As you've seen, the current gain could be as large as 50, whereas in fact the voltage gain of this amplifier is only 10.
Well, now for a different kind of amplifier. This is the current-derived feedback circuit described in the unit. You'll remember that I'm using RL as the load resistor. It's the voltage across this second resistor that's fed back. So the feedback voltage is proportional to the current through this resistor, and hence to the current through the load. This will always be true provided that the input current drawn by the amplifier is negligible. Once again, the scope is used to show the input and output voltages. I'll try a range of resistors. I have 10 kilo ohms connected. Now I'll try 1 kilo ohm. The output voltage, and hence the voltage gain, has decreased. I'll increase the scope sensitivity. And the gain changes by about 10. Now I'll try 100 ohms. And again, the voltage has decreased. And it also looks like a factor of about 10. Well, the voltage gain changes with load, but what about the current gain? Well, let's have a look. I can connect a digital meter here to measure the input current, and here to measure the output current. I've got a 100 ohm load, and the input current, well, we're reading in milliamps, so that's about 52 microamps. And the output current, it'll take a little time to settle, well, that's around 500 microamps. Now I'll try the 1 kilo ohm load. The output current, well, that's still around 500 microamps, and the input current, well, that's still around the 50 microamps. So the same as before, and the current gain hasn't changed. Now I'll try 10 kilo ohms. Well, the input current's the same, about 50 microamps, and the output current, well, that's actually settling at about 330, so it's dropped quite a bit. So the current gain changes if the load resistance is large, but not if it's small. I wonder how small. I'll try a short circuit. Well, the output current comes back up to the 500 microamps. And that was the same as the 100 ohms and the 1 kilo ohm. Let's look at our Thevenin equivalent of the amplifier output circuit again. If the volts dropped across the load RL are negligible compared with the volts dropped across R0, then RL won't affect the current. We'll effectively get the short circuit current so long as R0 is large compared with RL. As we've seen, the current wasn't affected when RL was 1 kilo ohm, so R0, the output resistance of the amplifier, must be large compared with 1 kilo ohm. Once again, we've built the circuit around the 741 amplifier with an open loop output resistance of about 75 ohms, but feedback has given us an amplifier with a much larger output resistance. This gives an output current, and hence a current gain, which is independent of the load over a wide range of load resistance. Though, as you saw, the voltage gain varied with low resistance. In fact, the voltage gain could be much larger than the current gain. This type of amplifier is used in applications where one wants the output current independent of load impedance. This applies, for instance, to magnetic tape recorders. What our two circuits show is that negative feedback can be used to control the output resistance of an amplifier, and in particular, to ensure that either its voltage gain or its current gain are independent of load over some specified range. We have also seen that an amplifier can have current and voltage gain. This illustrates a fundamental property of all amplifiers, namely that they increase signal power. They do this by converting power from their DC supplies into signal power. Power is current times voltage, so both current and voltage gain can increase power, and many amplifiers can give both types of gain. The point is that they always give power gain. Well, now for another effect of feedback.
This is an amplifier driven by a source fed in here. I'm going to use it to look at some of the effects of negative feedback on distortion. The input and output are shown on the scope, input and output. I'll superpose the two. Well, it's quite clear there's a lot of distortion. The form of the output is very different from that of the input. Let's concentrate on the output. I'll close the feedback loop. It's voltage-derived feedback like the first circuit in the unit. Well, the gain is reduced, so I'll increase the input to get back to where we started. Now, the output trace is looking very much more like a sinusoid, so negative feedback has removed the distortion introduced by the amplifier. As we'll be seeing in a moment, negative feedback cannot reduce all types, but the fact that it can reduce some types of distortion is very important in practice. Most amplifying devices are inherently nonlinear, and they can only be used to make linear amplifiers if suitable feedback is applied. Well, I've got another feedback circuit, but the distortion is rather different, as you can see from this output trace. The tops and bottoms of the waveform are flattened out. Now I'll close the loop. I'll just put in a resistor for R1. There wasn't one in before. The distortion has gone, but the output level has been reduced. So I'll do the same as before. I'll increase the input so as to get the same output level as I got without feedback. Well, the distortion is back again. What's happening is that we're getting saturation. The magnitude of the output voltage is not sufficient for the extreme parts of the peaks and troughs. The amplifier is being asked to produce more volts than it can give, and feedback cannot increase the maximum output voltage. So feedback's of no use in overcoming distortion effects due to saturation. But As you saw with the previous circuit, it can reduce distortion at voltage levels below saturation. Feedback is used a great deal for this purpose. A typical example is hi-fi amplifiers, in which, as you'll see in Unit 9, negative feedback is used to achieve the low distortion essential for high fidelity.
Well, I hope you've managed to do the home experiment on the Wien oscillator. Let me briefly describe the circuit. There is a feedback network called a Wien network. It has 2 resistors and 2 capacitors and is a form of potential divider. Its output provides the feedback which goes to the non-inverting input of the amplifier. Because of the 2 RC elements, the attenuation of the voltage divider is obviously going to be frequency dependent in both amplitude and phase. Now, as explained in Unit 6, oscillation will occur when the gain around the loop gain, has a modulus of 1, with 0 phase change around the loop. If these are the conditions, we have positive feedback. If you've already attempted SAQ 13 of Unit 6, you may remember that the attenuation of the Wien network is 1/3 at that frequency for which the phase change is 0. So to ensure a net gain of 1 around the loop, the amplifier must provide a gain of 3. As in the home experiment, I'm actually using one of the modules. I've nearly finished setting it up. This is the amplifier. Its output goes to the Wien network, and I can close the feedback loop going from the output of the amplifier to the input of the network. And if I get the gain right, you can see on the oscilloscope that it does indeed oscillate. I've measured this frequency, and it's about 700 Hertz. Now, I'd like to check this using a swept frequency source, because this is a very useful technique for measuring the loop gain of an amplifier system. This is the system. In order to measure loop gain, the loop has to be opened. Then a sine wave generator is connected to the amplifier input and a display unit to the Wien network output. The generator automatically sweeps over the range of frequencies I want to look at. As it sweeps from low to high frequencies, it also produces a voltage proportional to frequency, which is used to provide the X deflection of the display. The Y deflection can be set either to show the modulus of the loop gain or the phase change around the loop. Okay, so I'll just open up the loop again, and I'll connect my swept source to the amplifier input, and I'll take the output from the Wien network. And I'll just set up and start the display. The display is showing the modulus of the loop gain. This is the frequency for which the loop gain is unity. I've already done the phase sweep and stored it. Let me just show you. Now, this is the frequency for which the phase change around the loop is 0. It's the frequency for which the gain has a magnitude of 1. Let me bring back the magnitude display. And as you'd expect from the unit, it turns out to be about 700 Hertz, the frequency at which the circuit oscillates when the loop is closed. If you've already done the oscillator experiment in Unit 6, I'm sure you'll appreciate how useful and time-saving this kind of swept frequency technique can be. It is used a great deal in electronics.
Well, I hope this program has illustrated how important the idea of feedback is to electronics. As you've just seen, it can control the gain, the bandwidth, and the output resistance of an amplifier. It can cure certain types of distortion, and it can be used to turn an amplifier into an oscillator.
Well, that was the last of this morning's